In this example, we have star A, which has a mass of capital M. I'm going to draw that out like this. At a distance r from the star, the gravitational field strength is GS. So from the center of the star, we've got r distance, and the gravitational field strength is GS. Star B has a mass of 2m. What is the gravitational field strength at distance 3r from the star B in terms of GS? Okay, the fields of the two stars are not interacting. Okay, we can use the equation for gravitational field strength here like this, and the capital G, the constant. The mass of the second star compared to the first star is times 2, and the distance from the center is times 3. Okay, so but the 3 is being squared. So and that's at the bottom as well. So that becomes times 9. So overall, the gravitational field strength at this point we're looking for is going to be 2/9. So the gravitational field strength will be 2/9 GS. In this example, we have two identical uniform spheres, each of radius r, and they're in contact with each other. The gravitational force between them is F. Okay, so like this. So the same spheres, same radius, same mass. The force between them on each one is F due to gravity. Okay, the spheres are now separated until the force of attraction is F/4. So it's a quarter of the force from before. In terms of r, what is the distance between the surface of the spheres after they have been separated? So we've been separating the two spheres, and so the gravity between them, the gravitational attraction is weaker, is a quarter of the initial size, and we need to figure out the distance between the surfaces. So the initial distance between the centers of the two spheres was 2r. Okay, so the radius of both added together. Now we need to figure out this d, which is the surface between the distance between the surfaces. So we can use Newton's law of gravitation, which is F equals gmm over r squared, and I want the force to be a quarter. The G, M, and M are the same. We're not changing those. So those we can ignore those. Okay, so what do we need to do to the R in order to get a quarter on the other side? Well, let's try times 2, because the times 2 is going to get squared, and that's going to become times 4. And that's at the bottom, so we'd get a quarter on the other side. Another way to think about this is let's just make R the subject of the equation. So bring R to the other side, up to the top, and bring the F down and square root it. So we get this equation. And now, again, just ignore the G and the M's and everything. We want the force to be a quarter. A quarter is at the bottom, so it comes to the top, actually becomes times 4. You can think of that whole thing as being multiplied by 4. And that's under a square root. So it actually becomes times 2. Okay, so we want the radius to become times 2 compared to the initial setup. So if we want that to be times 2, we want to go from 2r to 4r. In order to be 4r, then the distance between the surfaces needs to be another 2r. Okay, that's the answer. Okay, question 3 here. Show the gravitational field strength G on the surface of a planet with radius capital R is given by this equation here. We've got 4 pi G rho R over 3, where rho is the average density of the planet. So let's start with the equation of gravitational field strength, Gm over R squared. I'm actually going to use capital R here for the distance from the center to the point, because I'm interested in the gravitational field strength on the surface of the planet. And instead of m for the mass of the planet, I'm going to use density equation, density times volume, where the volume here is the actual volume of the planet itself. So we can assume the planet is a sphere. So instead of the volume there, I'm going to use 4 over 3 pi r cubed, where r is the radius of the planet. So that's the volume of the sphere. Okay, if I put that into the equation, now I can cancel out a bunch of things. Actually, there's an r cubed at the top and an r squared at the bottom, so we can cancel out the r squared, and one of the two of the three r's at the top cancel out, and that gives us the equation that we're looking for. Okay, so we have part B of the same question here. Two planets P and Q are made from the same material. So straight away that tells me this density of these two planets is the same because they're made from the same material. Okay, the planet Q has a radius 1.5 times larger than planet P. Okay, so I'm going to draw this picture. So two planets, planet P has radius r, and then planet Q would have 1.5 times that radius. The gravitational field strength on the surface of planet P is 12 newtons per kilogram, and we need to figure out the gravitational field strength on the surface of planet Q. So we could use this equation, except we don't really know what's going on with mass. It's actually just quicker to use the equation that we just derived a minute ago, which has density in it. And in this equation, we can just ignore all of these numbers here, 4 pi g, density 3, because they're all constant, they're not changing between the two planets here. and it's a radius that's different. So the radius on the second planet is 1.5 times bigger, and as you can see, that's directly proportional to gravitational field strength. So the gravitational field strength is going to be 1.5 times bigger, so 12 times that, and we get 18 newtons per kilogram on the surface of planet Q.